humanity's galactic highways, journey through wormholes. For countless generations, humanity has cast its gaze skyward, captivated by the twinkling tapestry of stars. The dream of traversing the vast, inky expanse beyond our own solar system has always been a powerful motivator, fueling both scientific inquiry and imaginative storytelling. However, the sheer, unimaginable distances between even our closest celestial neighbors, let alone entire galaxies, have historically presented an insurmountable barrier. Light itself, the fastest traveler we know, takes millions of years to cross intergalactic voids, making conventional travel methods utterly impractical for such journeys. Yet, the intriguing and deeply theoretical concept of wormholes has emerged from the complex equations of physics, offering a tantalizing, albeit speculative, solution. These hypothetical shortcuts, tunnels through the fabric of spacetime, could fundamentally rewrite the rules of interstellar and intergalactic travel, potentially transforming what was once the exclusive domain of science fiction into a breathtaking, tangible scientific reality. The very thought ignites a profound sense of wonder and possibility, pushing the boundaries of what we believe is achievable. Einstein's legacy. The foundational concept of wormholes isn't a whimsical invention, but rather a fascinating byproduct of one of humanity's most profound scientific achievements, Albert Einstein's theory of general relativity. Published in 1915, this revolutionary theory redefined our understanding of gravity, not as a force, but as a curvature in the very fabric of spacetime caused by mass and energy. While Einstein's equations didn't explicitly predict the existence of wormholes, later interpretations and solutions to these complex mathematical expressions by physicists like Ludwig Flamm, Hermann Weyl, and notably Kip Thorne suggested that such bridges could theoretically exist. To grasp this abstract idea, imagine a simple analogy. Take a flat sheet of paper to represent the vastness of space-time. If you mark two distant points on this paper, a journey between them seems long. Now fold the paper and physically poke a hole directly through both marked points. This hole represents a wormhole, providing a vastly shorter path between two otherwise separated regions of space-time. The implications of such a cosmic shortcut are, quite literally, universe-changing. Exotic matter challenge. While the theoretical framework for wormholes exists, translating that theory into a practical reality faces a monumental hurdle: the requirement for exotic matter. This isn't just any unusual substance. Exotic matter is a hypothetical form of matter that possesses truly bizarre properties, most critically, negative energy density. Our everyday experience with matter involves positive energy density, which attracts gravitationally. However, to keep a wormhole's throat open and stable, preventing its own immense gravitational forces from collapsing it instantaneously, a powerful outward repulsive force is needed. This is where negative energy density comes into play. It would counteract the crushing inward pull of gravity, effectively propping the wormhole open for passage. The challenge is immense because, as of now, exotic matter has never been observed or proven to exist in the real universe. Its properties are purely theoretical, making its creation or discovery one of the most significant, if not the most significant, obstacles to wormhole travel. Without it, wormholes remain fascinating mathematical curiosities rather than viable cosmic pathways. Navigating the throat. Assuming humanity somehow overcomes the exotic matter challenge and manages to create a stable wormhole, the journey isn't over. Navigating the throat of the wormhole itself presents a new set of formidable engineering and physiological challenges. The region within a wormhole is predicted to be an environment of extreme gravitational gradients. These aren't just strong gravitational pulls, they are rapid, uneven changes in gravity that could subject any object, including a spacecraft and its occupants, to incredibly powerful tidal forces. Imagine being stretched and squeezed simultaneously in multiple directions, a truly catastrophic scenario for any biological organism or even the strongest materials. Theoretical models attempting to make wormhole travel plausible suggest that the wormhole's opening, or mouth, would need to be sufficiently wide, and its internal structure carefully managed to allow a spaceship to pass through without being torn apart. Engineers would face the unprecedented task of designing vessels capable of withstanding these forces, requiring materials and structural designs far beyond anything currently conceived. Time dilation concerns. Even if the structural integrity of a spacecraft and its crew could be maintained within a wormhole, another profound consequence of relativistic physics comes into play: time dilation. According to Einstein's theories, gravity and speed can affect the passage of time. While traveling through or near a wormhole, especially if it involves extreme gravitational fields or near light speeds relative to an external observer, time for those inside the wormhole could pass at a significantly different rate than for those who remain outside. Passengers might experience only a few moments, hours, or days during their journey, while back on Earth, decades, centuries, or even millennia could have elapsed. This time debt would have profound social, psychological, and technological implications. Returning to a world drastically changed, perhaps unrecognizable, would create an unprecedented form of cultural shock. Communication would become one-sided, with messages from Earth taking eons to reach the travelers, if ever. Humanity would need to grapple with these relativistic effects, developing new protocols for interstellar communication, family connections, and even the very definition of a return from such a journey. Mapping the cosmic web. Before any intrepid explorers could plunge into the unknown depths of a wormhole, an extensive and sophisticated program of cosmic cartography would be absolutely essential. The universe is a vast and unpredictable place, and blindly searching for these elusive tunnels would be a fool's errand. Astronomers would need to develop advanced observational techniques and instruments capable of identifying potential wormhole locations. This might involve searching for subtle gravitational anomalies that hint at space-time distortions, or detecting unusual energy signatures that align with theoretical predictions for the exotic matter or intense gravitational fields associated with wormholes. Regions exhibiting extreme gravitational lensing, where the light from distant objects is bent and magnified by massive foreground structures, could be prime candidates for closer inspection. Building a comprehensive cosmic web map of confirmed or highly probable wormhole locations would be an undertaking of epic proportions, requiring international collaboration and unprecedented data analysis capabilities. This meticulous preparation would be crucial for ensuring safe, efficient, and targeted travel through these potential intergalactic highways. Building the starships. Our current fleet of spacecraft, while marvels of engineering for interplanetary missions, are simply not equipped for the demands of intergalactic travel, even with the aid of wormholes. The journey to a wormhole's entrance, which itself could be light years away, would necessitate the development of entirely new classes of propulsion systems. We'd need to move far beyond chemical rockets, perhaps embracing concepts like fusion drives, antimatter propulsion, or even speculative warp drives, to reach a wormhole in a reasonable time frame. Furthermore, the vessels designed to actually traverse a wormhole would need to be incredibly resilient. They would have to withstand not only the intense radiation and vacuum of deep space, but also the unique and potentially violent forces associated with space-time manipulation and the presence of exotic energies. This would push material science, energy containment, and structural engineering to their absolute limits, requiring breakthroughs that are currently the stuff of theoretical physics. These would be true starships, built for journeys on scales we can barely comprehend. The intergalactic bridge. Imagine a future where humanity has successfully mastered wormhole travel, establishing a network of stable, traversable cosmic bridges. This wouldn't just be a localized phenomenon. It could form a vast intergalactic highway system, connecting our Milky Way to distant galaxies like Andromeda, Triangulum, and beyond. Such a development would fundamentally transform our species and our understanding of the universe. Humanity could establish outposts, research stations, and even new colonies in previously unreachable galaxies, fostering an unprecedented era of exploration and discovery. The exchange of knowledge, resources, and perhaps even cultural ideas with potential extraterrestrial civilizations, if encountered, would be immense. The very notion of home would expand to encompass multiple galaxies. This intergalactic bridge would not only satisfy our innate curiosity, but also provide insurance for the long-term survival of our species, diversifying our presence across the cosmos and safeguarding against any localized catastrophe. It would mark our transition from a planetary species to a truly galactic civilization. Edge of the universe. Wormholes, if they could be reliably created and navigated, might offer an even more profound possibility, a pathway to the very edge of the observable universe. While the concept of a true edge is complex and often misunderstood due to the ongoing expansion of the cosmos, wormholes could theoretically bypass the immense distances and cosmic expansion that currently limit our observational reach. By creating shortcuts through the accelerating expansion, these tunnels could allow us to glimpse regions of spacetime that are currently beyond our light horizon, areas whose light has not yet had time to reach us. This would be an unparalleled opportunity to study the earliest moments of the universe, observe primordial structures, and potentially uncover new secrets about the Big Bang, dark matter, and dark energy. The journey to what we perceive as the edge would not be about physically reaching a boundary, but rather about transcending the limitations of light-speed travel and cosmic expansion, revealing an entirely new perspective on the grand cosmic narrative and our place within its unfolding story. A future unimagined. The concept of humanity journeying through wormholes remains, for now, a profound scientific and engineering challenge, a tantalizing what-if at the bleeding edge of theoretical physics. The hurdles are immense: the elusive nature of exotic matter, the extreme forces within a wormhole's throat, the relativistic effects on time, and the sheer scale of the engineering required. Yet, the potential rewards are equally immense and undeniably inspiring. The promise of boundless exploration, the possibility of encountering new civilizations, and the opportunity to gain a deeper, more comprehensive understanding of the cosmos fuel our relentless pursuit of knowledge and technological advancement. While the practical realization of wormhole travel may be centuries or even millennia away, the very act of contemplating such a future drives innovation in every scientific field. The future of humanity, its destiny among the stars, may well be inextricably linked to these incredible, hypothetical cosmic shortcuts, opening doors to a future truly beyond our current imagination.